Does your consciousness create reality by collapsing quantum wave functions, making you an active participant in bringing the physical world into existence through observation? Or is this entire idea pseudoscientific nonsense that exploits mysterious quantum mechanics and equally mysterious consciousness to make profound-sounding claims without evidence? This question sits at the uncomfortable intersection of physics and philosophy, where some serious scientists propose radical ideas about consciousness playing a fundamental role in quantum mechanics, while other equally serious scientists dismiss these proposals as confused, thinking that misunderstands both quantum physics and neuroscience. The debate has raged for nearly a century since quantum mechanics was formulated, and it remains unresolved today despite enormous progress in our understanding of both quantum systems and brain function. The reason this question persists is deeply frustrating from a scientific perspective. We cannot definitively prove the quantum consciousness hypothesis wrong, even though most physicists believe it is wrong. The hypothesis is essentially unfalsifiable, meaning no experiment can conclusively rule it out, because any negative result can be explained away by claiming we measured the wrong thing, or looked in the wrong place, or did not understand the subtle ways consciousness interacts with quantum systems. This makes quantum consciousness different from most scientific theories, which make specific testable predictions that can be confirmed or refuted through experiment. Instead, quantum consciousness occupies an uncomfortable middle ground, where it seems unlikely to be true based on what we know about physics and neuroscience, yet cannot be eliminated as a possibility, because consciousness and quantum measurement both involve deep mysteries we do not fully understand. Understanding why this idea gained traction requires examining the genuine mysteries at the heart of quantum mechanics and consciousness separately, before considering whether connecting them illuminates anything or simply combines two mysteries into one bigger confusion. The measurement problem in quantum mechanics is real and has troubled physicists since the 1920s. Quantum systems exist in superposition, meaning they simultaneously occupy multiple states until measured, at which point the superposition collapses to one definite outcome. Schrödinger's famous cat is both alive and dead until someone opens the box and observes it, causing the wave function to collapse to either alive or dead, but not both. This is not merely a thought experiment, but describes actual quantum behavior, confirmed by countless experiments with particles, atoms, and increasingly large molecules. The disturbing question is, what counts as a measurement? What causes wave function collapse? Does the quantum system simply need to interact with any physical apparatus, or does conscious observation specifically play a role? Copenhagen interpretation, the standard textbook view, says measurement causes collapse, but never precisely defines what constitutes measurement or why measurement is special. This vagueness has frustrated physicists for generations. Some early quantum pioneers, including Eugene Wigner and John von Neumann, proposed that consciousness might be the answer, that conscious observation is what fundamentally distinguishes measurement from ordinary physical interaction and causes the wave function to collapse. Von Neumann's famous argument involved an infinite regress problem. A quantum particle exists in superposition until measured by an apparatus. But the apparatus is also a physical system described by quantum mechanics, so it too can be in superposition of having measured different outcomes until someone observes the apparatus. But that observer is also a physical system that could be in superposition until observed by someone else, and so on infinitely. This chain must stop somewhere, and von Neumann proposed it stops at consciousness, which he argued exists outside the quantum mechanical description and causes definite outcomes to manifest when conscious beings observe quantum systems. This would mean consciousness plays a fundamental role in physics, not merely as an emergent property of complex brains, but as a basic feature of reality required to collapse wave functions and create definite outcomes from quantum possibilities. Observation would not merely reveal pre-existing facts, but would actively create facts by forcing quantum systems to choose definite states. Reality would be participatory, requiring conscious observers to bring it into definite existence. This is a profound claim about the nature of reality that elevates consciousness from interesting biological phenomenon to fundamental physical necessity. But most physicists today reject this interpretation despite its prestigious early advocates. The main reason is decoherence, a process discovered in the 1970s and 1980s that explains wave function collapse without invoking consciousness. Decoherence shows that quantum systems interact with their environment constantly, and these interactions cause superposition to effectively disappear extremely rapidly for all but the most isolated systems. A quantum particle in a lab is constantly bombarded by air molecules, photons, and thermal radiation. Each interaction entangles the particle's quantum state with the environment's quantum state, spreading quantum information into the environment and making superposition effectively impossible to observe. The wave function does not technically collapse but becomes so entangled with environment that the system behaves as if it has definite properties. Decoherence happens incredibly fast, typically in femtoseconds or picoseconds, for any system larger than individual particles in vacuum. This explains why we never observe superposition in everyday objects, despite everything being quantum mechanical at a fundamental level. The cat in Schrödinger's thought experiment cannot actually be in superposition of alive and dead, because decoherence from air molecules and thermal radiation would destroy any superposition essentially instantaneously. The measurement problem is not about consciousness, but about how quantum systems interact with their environment, and consciousness is not required to explain why definite outcomes emerge. This would seem to settle the question decisively against quantum consciousness theories, yet they persist for several reasons. First, decoherence does not completely solve the measurement problem. It explains why we observe definite outcomes rather than superposition in practice. But philosophical questions remain about whether wave functions actually collapse or whether all possibilities remain real in some sense, as in many worlds interpretation. Second, the hard problem of consciousness remains unsolved. We have no physical theory explaining why subjective experience exists or how objective brain processes produce the subjective feeling of what it is like to be conscious. This explanatory gap makes consciousness seem mysterious and potentially non-physical, raising the possibility that consciousness operates by different rules than ordinary matter. Third, some respectable scientists continue proposing quantum consciousness theories, most famously physicist Roger Penrose and anesthesiologist Stuart Hameroff with their orchestrated objective reduction theory. Penrose won the Nobel Prize in Physics in 2020 for his work on black holes, lending credibility to his quantum consciousness proposals, even though they are highly controversial, and most physicists reject them. The persistence of such theories from serious researchers rather than fringe pseudoscientists makes dismissing quantum consciousness more complicated than dismissing, say, astrology or homeopathy. Penrose argues that consciousness cannot be explained by classical computation because of Gödel's incompleteness theorem and our ability to understand mathematical truths that cannot be proven by any algorithm. He claims consciousness must involve non-computable quantum processes, specifically quantum gravity effects causing objective collapse of wave functions in the brain. Hameroff proposes that microtubules, tiny protein structures forming the cytoskeleton inside neurons, could maintain quantum coherence long enough to perform quantum computation underlying consciousness. Together, they developed orchestrated objective reduction, proposing that quantum superposition in microtubules collapses due to quantum gravity effects, approximately 40 times per second, producing moments of conscious awareness. This is a specific scientific proposal that should be testable in principle, but testing it has proven extraordinarily difficult. The main objection is that decoherence should destroy any quantum coherence in microtubules essentially instantly because the brain is a warm, wet, noisy environment completely unsuitable for maintaining delicate quantum states. Room temperature and biological molecules bouncing around should cause decoherence in femtoseconds, while neural processes and consciousness operate on timescales of milliseconds. The theory requires quantum coherence to survive 1 trillion times longer than physics calculations suggest is possible in brain conditions. Penrose and Hameroff respond that the brain might have evolved special mechanisms to protect quantum states from decoherence, perhaps through specially structured water molecules or quantum error correction or other exotic processes. They point to recent discoveries that some biological systems like photosynthesis use quantum coherence, even at room temperature, suggesting biology might be more quantum than previously thought. But these discoveries involve carefully structured protein complexes that isolate quantum systems much better than brain conditions would allow. And even in photosynthesis, coherence lasts only picoseconds. No experimental evidence has confirmed quantum effects in microtubules or anywhere else in the brain despite decades of searching. Microtubules have been studied extensively because they are important for cell structure and function, but nothing suggests they maintain quantum coherence or perform quantum computation. This lack of evidence after 30 years since the theory was proposed should be damning, yet the theory persists because it cannot be definitively disproven. You can always claim the measurements are not sensitive enough or looking in the wrong places or not understanding subtle quantum effects that escape current detection. This brings us to the fundamental problem with quantum consciousness theories. They are essentially unfalsifiable. If experiments find no quantum effects in the brain, proponents can say we have not looked carefully enough or in the right places. If experiments show classical neural networks can explain cognition without quantum mechanics, proponents can say consciousness involves something beyond cognition. If decoherence calculations show quantum coherence is impossible in brain conditions, proponents can invoke unknown protective mechanisms. Every objection can be met with speculative responses that are impossible to test, making the theory immune to empirical refutation. Unfalsifiable theories are problematic for science because science progresses by testing predictions and rejecting theories that fail tests. A theory that can accommodate any possible observation by adjusting its assumptions is not making genuine contact with reality, but is instead a flexible framework that can be molded to fit whatever evidence appears. This is the hallmark of pseudoscience, the ability to explain anything while predicting nothing specific that could prove the theory wrong. By this standard, quantum consciousness theories look more like pseudoscience than science, despite being proposed by credentialed physicists and published in academic journals. Yet, the situation is more nuanced than simply dismissing quantum consciousness as pseudoscience. The hard problem of consciousness is genuinely unsolved. We do not have a physical theory explaining subjective experience. We do not understand why brain processes feel like anything from the inside. This is not merely ignorance we will fill in as neuroscience progresses, but maybe a fundamentally different kind of problem requiring radically new physics. Many philosophers and some scientists argue that consciousness cannot be explained purely through physical processes because there is an explanatory gap between objective descriptions of brain activity and subjective experience of what that activity feels like. If consciousness really cannot be reduced to physics as currently understood, then something is missing from our physical theories. Perhaps consciousness involves quantum processes we do not understand. Perhaps it involves new physics beyond the standard model. Perhaps it involves some fundamentally non-physical aspect of reality that interacts with physical systems in ways we have not discovered. These are speculative possibilities, but they cannot be ruled out completely because consciousness remains mysterious despite enormous neuroscientific progress. The measurement problem in quantum mechanics also remains genuinely unresolved depending on which interpretation you accept. Copenhagen interpretation leaves measurement undefined and vague. Many worlds interpretation avoids collapse by saying all outcomes occur in different branches of reality, which many find extravagant and philosophically troubling. Objective collapse theories like Penrose proposes say collapse happens spontaneously, without observation. But we have no empirical evidence for such spontaneous collapse and no confirmed theory of quantum gravity to predict it. Pilot wave theories restore determinism, but require faster-than-light influences and seem contrived. Every interpretation has problems, leaving fundamental questions about quantum mechanics unresolved after a century of trying. So we face two deep mysteries, consciousness and quantum measurement, neither of which we fully understand despite intensive research. The temptation to connect them is psychologically understandable even if scientifically questionable. Maybe the mysteries are related. Maybe understanding one would illuminate the other. Maybe consciousness and quantum mechanics are two sides of the same coin. This feels profound and appealing, but feeling profound does not make an idea true. Many profound-sounding ideas turn out to be wrong when tested carefully. In the next part, I will examine specific quantum consciousness theories in detail, showing exactly how they propose consciousness affects quantum systems, and why these proposals face serious objections from mainstream physics and neuroscience. I will show that quantum consciousness theories make specific claims that should be testable but have never been confirmed despite decades of research. And I will explain why these theories persist despite lack of evidence, revealing the sociological and psychological factors that keep ideas alive long after empirical support disappears. Understanding the quantum consciousness debate requires examining not just the science but the human factors that make certain ideas attractive regardless of whether they are actually correct. Let me show you exactly what quantum consciousness theories claim and why they are simultaneously intriguing enough to attract serious scientists and implausible enough that most physicists reject them. The most famous and detailed proposal is orchestrated objective reduction, or Orch OR, developed by mathematical physicist Roger Penrose and anesthesiologist Hameroff. This theory has been refined over 30 years and represents the most sophisticated attempt to connect quantum mechanics with consciousness. Understanding why Orch OR was proposed and why it faces serious objections reveals the difficulties of making quantum consciousness scientifically respectable rather than pseudoscientific speculation. Roger Penrose is not a fringe figure, but one of the most accomplished mathematical physicists alive. He made fundamental contributions to general relativity and black hole physics, shared the 2020 Nobel Prize in Physics for proving that black holes are inevitable consequences of Einstein's equations, and has written influential books on mathematics, physics, and consciousness. When someone with Penrose's credentials proposes a radical theory, it demands serious attention, even if ultimately wrong. His quantum consciousness theory originates from mathematical arguments about computation and consciousness rather than from quantum mechanics directly. Penrose's starting point is Gödel's incompleteness theorem, one of the most important results in mathematical logic. Kurt Gödel proved in 1931 that any consistent formal system powerful enough to describe arithmetic contains true statements that cannot be proven within that system. This means mathematical truth transcends provability by any algorithm or mechanical procedure. You can always construct statements that are true but cannot be proven by following rules, implying that mathematical understanding involves something beyond computation. Computers operate algorithmically by following programmed rules, so Gödel's theorem suggests that mathematical insight requires non-algorithmic processes. Penrose argues that human mathematicians can recognize mathematical truths that cannot be proven algorithmically, such as recognizing that certain Gödelian statements are true despite being unprovable within their formal systems. This ability, he claims, shows that human consciousness involves non-computable processes that cannot be simulated by any computer following algorithms. Since classical physics is computable in principle, you can simulate Newtonian mechanics or even chaotic systems on a computer. Given enough time and precision, consciousness cannot be explained purely by classical brain processes. Something non-computable must be happening in the brain, and the only known source of non-computable physics is quantum mechanics combined with gravitational effects. This argument has been heavily criticized by philosophers and computer scientists, who argue that Penrose misunderstands Gödel's theorem and underestimates what classical computation can achieve. They point out that humans make mathematical errors, sometimes accepting false proofs and rejecting true statements, which suggests our mathematical reasoning is fallible and heuristic rather than based on perfect non-computable insight. They argue that classical neural networks using probabilistic algorithms can approximate mathematical reasoning without requiring quantum effects. Penrose has defended his position against these criticisms, but most experts in computation and artificial intelligence remain unconvinced that Gödel's theorem proves consciousness is non-computable. Nevertheless, accepting Penrose's argument for the sake of exploring the theory, if consciousness requires non-computable quantum processes, where in the brain could such processes occur? This is where Stuart Hameroff enters the story with microtubules. Hameroff is an anesthesiologist who has studied how anesthetic drugs cause loss of consciousness. He noticed that many anesthetics bind to microtubules, tiny protein structures that form the cytoskeleton inside neurons and all other cells. Microtubules are hollow tubes assembled from tubulin protein subunits arranged in geometric lattices. Each subunit can exist in different conformational states, potentially creating a complex information processing system within each neuron beyond the standard neuron firing patterns. Hameroff proposed that microtubules might be the site of quantum computation in the brain. The tubulin subunits could maintain quantum superposition of different conformational states, and quantum information could process through the microtubule lattice faster and more efficiently than classical neural signals. If many tubulin subunits become quantum entangled, they could perform massively parallel quantum computation, inaccessible to classical systems. This quantum processing would supplement the classical computation of neural firing patterns, providing the non-computable element that Penrose argues consciousness requires. Penrose and Hameroff combine these ideas into orchestrated objective reduction. The theory proposes that tubulin proteins in microtubules maintain quantum superposition of conformational states through quantum coherence. These superpositions are orchestrated by cellular processes, meaning they are not random but are guided and controlled by the neuron's biochemistry and structure. The orchestrated superposition grows, involving more tubulin subunits and extending across microtubules in multiple neurons through gap junction connections that link neurons directly. As the superposition grows, it also grows in mass energy because each tubulin protein has mass, and superposed states involve slightly different distributions of that mass in space-time. Here is where quantum gravity enters. Penrose had proposed in the 1990s, before collaborating with Hameroff, that quantum superposition cannot be maintained indefinitely when significant mass is involved, because superposed states create different space-time geometries. General relativity says mass curves space-time, so a particle in superposition of being in two different locations creates superposition of two different space-time curvatures. Penrose argued that such space-time superposition is unstable and will spontaneously collapse to one outcome or the other, after a time inversely proportional to the mass involved. This is objective reduction, objective because it happens spontaneously without requiring external measurement, and reduction because superposition reduces to a single definite state. The mathematics gives a specific relationship. The collapse time equals Planck time multiplied by the Planck mass squared divided by the mass energy difference between the superposed states. For a single particle, this time is astronomically long, far longer than the age of the universe. But for larger masses, or for systems involving many particles in coordinated superposition, the collapse time becomes much shorter. Penrose calculated that for microtubules with thousands of tubulin proteins in coordinated superposition, the collapse time would be around 25 milliseconds, which happens to be close to the timescale of conscious moments and gamma wave oscillations in the brain. Orch OR proposes that consciousness arises from this quantum collapse process. Superposition builds in microtubules across neurons. When it reaches the threshold where quantum gravity effects cause spontaneous collapse, a moment of conscious experience occurs. The collapse is not random but is orchestrated to produce outcomes relevant to the organism's needs based on the orchestration from cellular structures. The theory predicts consciousness occurs in discrete moments at roughly 40 times per second, matching 40 Hz gamma oscillations observed in brain activity during conscious awareness. Between these moments, the brain operates unconsciously, building quantum superposition that then collapses into the next conscious moment. This would explain why consciousness feels unified despite the brain containing billions of neurons. Quantum coherence and entanglement could bind many neurons into a single quantum state that collapses simultaneously, producing unified conscious experience rather than millions of separate neural events. It would explain the difference between conscious and unconscious processing. Conscious processing involves quantum coherence and collapse, while unconscious processing is purely classical. It would explain why anesthetics cause unconsciousness. They interfere with quantum coherence in microtubules, preventing the buildup of superposition necessary for consciousness. It would explain free will. Quantum randomness in the collapse process introduces unpredictability that could enable genuine choice rather than deterministic neural computation. If true, Orch OR would be revolutionary. It would solve the hard problem of consciousness by identifying the physical basis of subjective experience. It would connect quantum mechanics and general relativity through quantum gravity effects in the brain. It would show that consciousness plays a fundamental role in physics through quantum collapse. It would prove human minds are quantum computers that cannot be simulated classically. It would validate Penrose's non-computability argument. It would explain numerous mysteries about consciousness in one unified framework. This explanatory ambition is both the theory's appeal and its greatest weakness. It claims to explain too much, too neatly, which raises suspicions. The theory faces devastating objections that have convinced most physicists it is wrong. The primary objection concerns decoherence. Quantum coherence is extraordinarily fragile and is destroyed by interaction with the environment. The brain is possibly the worst environment imaginable for maintaining quantum coherence. It operates at body temperature, roughly 300 degrees Kelvin, meaning molecules have enormous thermal energy and bounce around rapidly. It is mostly water with dissolved ions, creating a noisy chemical soup. It is constantly active, with electrical signals, neurotransmitter releases, ion flows, and metabolic processes. Every one of these factors causes decoherence. Physicists have calculated decoherence times for various systems under different conditions. For quantum computers, maintaining coherence requires cooling to nearly absolute zero and isolating qubits from all external interaction using sophisticated shielding. Even then, coherence lasts only milliseconds before environmental noise destroys it. Scaling up to larger quantum systems makes decoherence worse, not better, because more particles mean more interaction with the environment. For biological molecules at body temperature surrounded by water and ions, decoherence calculations give timescales of femtoseconds to picoseconds at most. A femtosecond is 1/millionth of 1/billionth of a second. A picosecond is 1,000th of 1/billionth of a second. Orch OR requires quantum coherence to last 25 milliseconds, which is 25 thousandths of a second. This is about 10 trillion times longer than decoherence calculations suggest is possible in brain conditions. To put this in perspective, it is like claiming a snowflake could survive intact at the center of the sun for 25 minutes. The conditions are simply incompatible with maintaining the delicate quantum state. No known mechanism could protect microtubules from decoherence for the required time, given the hostile environment of the living brain. Penrose and Hameroff have responded to this objection in various ways over the years. They point out that decoherence calculations make assumptions about how microtubules interact with their environment, and perhaps those assumptions are wrong. Perhaps microtubules are specially structured to shield quantum states from decoherence through ordered water molecules creating quantum isolation, or through quantum error correction mechanisms evolved specifically to protect coherence. They cite recent discoveries of quantum coherence in photosynthesis and bird navigation, as evidence that biology can maintain quantum effects at room temperature better than physicists expected. But these examples are not convincing to critics. Photosynthesis does maintain quantum coherence at room temperature, which was surprising when discovered, but the coherence lasts only picoseconds and occurs in carefully structured protein environments designed by evolution specifically to exploit quantum effects for efficient energy transfer. The coherence times are still far shorter than Orch OR requires, and the systems are far more isolated than brain microtubules. Bird navigation might use quantum effects in specialized proteins in the eye, but again these would be carefully structured molecules evolved for that specific purpose and operating on very short timescales, nothing like the massive quantum computation Orch OR proposes throughout the brain. Moreover, if the brain had evolved mechanisms to protect quantum coherence so effectively that it survives 25 milliseconds at body temperature in a noisy chemical environment, this would be the most remarkable discovery in quantum physics. It would revolutionize quantum computing, allowing quantum computers to operate at room temperature without expensive cooling and isolation. Yet no evidence of such mechanisms exists. Microtubules have been studied extensively because they are important for cell division, transport, and structure. Nothing in decades of research suggests they maintain quantum coherence or perform quantum computation. They behave entirely classically, as far as any measurement can determine. Another serious objection concerns the lack of positive evidence. Orch OR makes specific predictions that should be testable. It predicts quantum coherence in microtubules lasting milliseconds. It predicts quantum entanglement linking tubulin proteins across neurons. It predicts anesthetics disrupt quantum coherence. It predicts gamma oscillations are synchronized with quantum collapse events. It predicts consciousness involves non-computable quantum processes. After 30 years, none of these predictions have been confirmed experimentally. Scientists have looked for quantum effects in microtubules. They have tested whether anesthetics affect microtubules in ways consistent with quantum disruption. They have searched for correlations between gamma oscillations and quantum processes. They have examined whether consciousness shows signatures of quantum computation. Every test has failed to find the predicted quantum effects. Some experiments initially appeared to show results consistent with Orch OR, but follow-up studies showed the results were artifacts or could be explained classically without quantum mechanics. No clear positive evidence exists after 3 decades of the theory being available for testing. Hameroff argues that current experimental techniques are not sensitive enough to detect the subtle quantum effects Orch OR predicts, and that future technology will vindicate the theory. This response exemplifies the unfalsifiability problem. If experiments find nothing, the response is always that we have not looked carefully enough or in the right way. This makes the theory immune to refutation through negative results, which is not how science should work. Theories should make bold predictions that risk being proven wrong. When those predictions fail repeatedly, we should lose confidence in the theory rather than claiming we have not tested it properly yet. Alternative explanations for consciousness exist that do not require quantum mechanics. Classical neural network models explain enormous amounts of cognitive function, including perception, memory, learning, language, reasoning, and decision-making, without invoking quantum effects. Neuroscience has made tremendous progress understanding how brain circuits produce complex behaviors through classical, electrical, and chemical signaling. While we do not yet understand how neural activity produces subjective experience, nothing about consciousness seems to require quantum mechanics, except for Penrose's controversial argument about non-computability. Artificial intelligence systems using classical computation are becoming increasingly sophisticated at tasks that seem to require intelligence and understanding. Large language models can engage in conversations, answer questions, write creatively, and solve problems in ways that superficially resemble human cognition. These systems are entirely classical computers with no quantum effects, yet they exhibit behaviors that once seemed to require human consciousness. This suggests consciousness might not be as special or non-computable as Penrose claims, but rather might emerge from sufficiently complex classical information processing. The philosophical objection is that explaining behavior and function is different from explaining subjective experience. Even if classical neural networks can reproduce all the cognitive functions of consciousness, they may not explain why those functions feel like anything from the inside. This is the hard problem of consciousness, explaining qualia, the subjective qualities of experience. Functionalist approaches that explain what consciousness does leave unexplained why it feels like something to do those things. Penrose and Hameroff argue quantum effects are necessary to cross this explanatory gap, but critics respond that adding quantum mechanics just adds another layer of complexity without actually explaining subjective experience. Other quantum consciousness theories exist beyond Orch OR, though none as detailed or widely discussed. Physicist Matthew Fisher proposed that quantum entanglement between phosphorus nuclear spins in molecules called Posner clusters might survive long enough in the brain to affect neural processing. Unlike Orch OR, which requires millisecond coherence, Fisher's proposal needs only microsecond to millisecond coherence, which is more plausible, though still difficult given brain conditions. Posner clusters are calcium phosphate molecules that could protect phosphorus nuclei from decoherence long enough for entanglement to influence neurotransmitter release. This is more conservative than Orch OR, but still lacks experimental confirmation. Some theorists propose that quantum tunneling in ion channels affects neural firing patterns in ways relevant to consciousness. Ion channels are proteins that allow ions to cross neuron membranes, and their opening and closing involves conformational changes that might have quantum mechanical aspects. Quantum tunneling could allow ions to cross barriers they classically could not, potentially influencing when neurons fire. But calculations suggest such tunneling effects average out statistically and do not create coherent quantum computation required for quantum consciousness theories. The effects would be noise rather than functional quantum information processing. Others propose consciousness is itself a quantum field analogous to electromagnetic or gravitational fields. The brain would interact with this consciousness field like a radio receiver interacts with radio waves. Conscious experience would not be produced by the brain, but by the brain tuning into the quantum consciousness field. This is essentially dualism repackaged in quantum language, proposing that consciousness is fundamentally separate from physical matter. It is completely untestable because the consciousness field could have whatever properties you want to postulate without constraint from observation. This makes it not even wrong in the sense that wrong theories at least make testable predictions that fail, whereas unfalsifiable theories cannot fail because they predict nothing specific. The appeal of quantum consciousness theories comes from several sources. First, both quantum mechanics and consciousness are mysterious, and connecting mysteries feels like progress even if it merely combines confusion. Second, quantum mechanics seems weird and non-intuitive, while consciousness also seems weird and non-intuitive, suggesting they might share some deep connection. Third, materialist explanations of consciousness seem inadequate to many people, who feel subjective experience cannot be just brain activity, and quantum mechanics offers something non-classical and potentially non-materialist. Fourth, quantum consciousness elevates human consciousness to fundamental importance in physics, rather than treating it as mere epiphenomenon of matter, which is emotionally satisfying. Fifth, quantum consciousness theories are proposed by credentialed scientists and published in academic journals, giving them legitimacy that pure pseudoscience lacks. When a Nobel Prize winner like Penrose proposes quantum consciousness, it cannot be dismissed as easily as crystal healing or astrology. Sixth, the theories cannot be definitively proven wrong because they are unfalsifiable, allowing believers to maintain faith despite lack of evidence. Seventh, quantum consciousness sells books and attracts media attention, creating incentives for promoting the ideas regardless of scientific merit. but appeal and plausibility are different. Quantum consciousness theories might feel profound and might connect concepts that intrigue us, but scientific truth is determined by evidence and empirical testing, not by how satisfying or elegant ideas seem. After 30 years, quantum consciousness theories have produced no confirmed predictions, no experimental validation, and no technological applications. They remain speculative proposals that most physicists reject because the physics and neuroscience do not support them. The fact that they cannot be definitively disproven does not make them scientifically valuable, but rather makes them unscientific because science requires falsifiability. In the final part, I will examine why these theories are most likely wrong but cannot be completely ruled out, and what this tells us about the limits of science when dealing with consciousness. I will show that the persistence of quantum consciousness theories, despite lack of evidence, reveals important truths about how science works socially and psychologically, not just logically. And I will address what the quantum consciousness debate means for understanding ourselves, whether we are classical information processors that happen to be conscious, or whether consciousness involves some quantum magic that makes us fundamentally different from any machine we might build. The answer matters not just intellectually but existentially. We must now confront the central question directly. Are quantum consciousness theories legitimate science operating at the frontier of knowledge, or are they pseudoscience dressed in mathematical formalism and scientific credentials? This distinction matters enormously because it determines whether resources should continue flowing toward quantum consciousness research, whether the ideas should be taught to students as serious possibilities, and whether we should take claims about consciousness, creating reality through quantum measurement seriously, or dismiss them as confused thinking. The uncomfortable truth is that quantum consciousness theories occupy an ambiguous zone between science and pseudoscience, having some characteristics of each, making definitive classification difficult and contentious. Let me lay out systematically why quantum consciousness theories are almost certainly wrong, then explain why we cannot prove them wrong definitively, and finally examine what this paradox reveals about the limits of science when confronting consciousness. Understanding this requires being brutally honest about both the scientific evidence and the philosophical complexities that keep these theories alive despite lack of empirical support. The case against quantum consciousness is overwhelming when examined objectively. Start with decoherence, the most devastating objection. Quantum coherence requires isolation from environmental interaction because any interaction entangles the quantum system with its environment, spreading quantum information outward and destroying superposition. The decoherence rate depends on temperature, system size, and environmental coupling. Brain conditions are essentially worst case for maintaining coherence. Body temperature of 300 Kelvin means enormous thermal energy with molecules moving at hundreds of meters per second. Water molecules, ions, proteins, and metabolites constantly collide with everything. Electrical activity, chemical reactions, and metabolic processes create a phenomenally noisy environment. Every calculation shows decoherence should occur in femtoseconds to picoseconds at most. Quantum consciousness theories require coherence, lasting milliseconds, which is 10 to 12 orders of magnitude longer than physics predicts possible. This is not a minor discrepancy, or a factor of 2, or even a factor of 1,000. This is 1 trillion times longer than calculations allow. To put this impossibly large gap in perspective, it is like claiming a soap bubble could remain intact in a hurricane for a year. The physics simply does not permit it given known mechanisms and environmental conditions. Claiming the brain has unknown protection mechanisms that overcome decoherence by a factor of 1 trillion is not a modest adjustment, but an extraordinary claim requiring extraordinary evidence, which does not exist. Proponents point to quantum biology examples like photosynthesis and bird navigation, where quantum coherence occurs at room temperature, but these examples do not support quantum consciousness. Photosynthesis maintains coherence for picoseconds in highly specialized protein structures evolved specifically to exploit quantum effects for energy transfer. The proteins create shielded environments isolating quantum systems from the surrounding chaos. Even with such specialized protection evolved over billions of years, coherence lasts only picoseconds. Bird navigation might use quantum effects in specialized proteins in the retina, but again, these would be carefully structured molecules evolved for that specific function. Nothing like the brain-wide quantum computation, quantum consciousness theories propose. If the brain could protect quantum coherence for milliseconds throughout its volume at body temperature, this would revolutionize quantum computing. Quantum computers currently require cooling to millikelvin temperatures just thousandths of a degree above absolute zero, and even then maintain coherence for only milliseconds with enormous effort. If neurons can do this naturally at 300 Kelvin without special cooling or isolation, we should be able to build quantum computers that operate at room temperature with no cooling infrastructure. The fact that no one has discovered how to do this despite billions invested in quantum computing research suggests strongly that the brain does not actually maintain such coherence. The second devastating problem is complete absence of positive evidence. 30 years after Orch OR was proposed, no experiment has confirmed quantum effects in microtubules relevant to consciousness. Scientists have looked. They have tested microtubules in vitro and in neurons. They have searched for quantum coherence, quantum entanglement, and quantum computation. They have examined whether anesthetics affect microtubules in quantum-relevant ways. Every search has come up empty. Some experiments initially suggested results consistent with quantum effects, but follow-up studies showed these were artifacts or had classical explanations not requiring quantum mechanics. This pattern of null results should be fatal for any scientific theory. When predictions fail repeatedly, science normally rejects theories regardless of how elegant or appealing they are. The lack of evidence after 30 years means either the experiments are insufficiently sensitive or the predicted effects do not exist. Quantum consciousness proponents always choose the first interpretation, claiming technology has not yet reached the necessary sensitivity. But this is an unfalsifiable response. If experiments find nothing, the answer is always that we have not looked carefully enough. This makes the theory immune to empirical refutation, which is the hallmark of pseudoscience, not science. Consider by contrast how quickly other quantum biological effects were confirmed once suggested. When quantum coherence in photosynthesis was proposed in the 1990s, experiments confirmed it within a decade using femtosecond spectroscopy. When quantum effects in bird navigation were proposed, experiments designed tests within years. When other quantum phenomena are predicted, science tests them promptly and reaches conclusions. The fact that quantum consciousness has resisted confirmation for 30 years despite active searching suggests the effects simply are not there to be found, not that our instruments are inadequate. The third problem is that classical explanations suffice. Neuroscience has made enormous progress explaining cognition, perception, memory, learning, and behavior using classical neural networks operating through conventional electrical and chemical signaling. While subjective experience remains unexplained, the functional aspects of consciousness, what it does, rather than why, it feels like something are increasingly understood classically. Nothing about cognitive function seems to require quantum mechanics. The only argument for quantum necessity is Penrose's claim about non-computability based on Gödel's theorem, which most computer scientists and philosophers reject as confused, thinking that misunderstands both Gödel's theorem and human mathematical reasoning. Artificial intelligence demonstrates that classical computation can produce sophisticated intelligent behavior without quantum effects. Large language models engage in conversations, answer questions, solve problems, and create content in ways that superficially resemble human intelligence. These are entirely classical systems with zero quantum computation, yet they exhibit behaviors that once seemed to require consciousness. This suggests consciousness might not be fundamentally different from complex classical information processing. contradicting the quantum consciousness claim that classical computation cannot explain consciousness. The counter-argument is that AI systems are not conscious, regardless of their impressive capabilities, because consciousness involves subjective experience that no amount of functional sophistication produces. This is the hard problem of consciousness. Even if we explain all cognitive functions classically, we have not explained why those functions feel like something from the inside. Quantum consciousness proponents argue that quantum effects are necessary to bridge this explanatory gap between function and experience. But this argument assumes the gap requires some special physics to bridge, when it might instead be a conceptual confusion about what kind of explanation consciousness requires. The fourth problem is that adding quantum mechanics does not actually solve the hard problem. Suppose Orch OR is correct, and consciousness involves quantum coherence in microtubules collapsing due to quantum gravity effects. Why would this quantum process produce subjective experience? Why does quantum coherence feel like something while classical neural activity does not? The theory does not answer this. It merely relocates the mystery from classical to quantum processes without explaining why quantum processes should be conscious while classical processes are not. This is sometimes called the quantum chauvinism objection, the unjustified assumption that quantum mechanics has some special relationship to consciousness that classical mechanics lacks. Penrose argues objective reduction is special because it is non-computable and fundamentally random, introducing genuine unpredictability that could enable free will. But why would non-computability or randomness produce consciousness? Computer randomness through quantum random number generators does not make computers conscious. Radioactive decay is fundamentally quantum and random, but no one thinks uranium atoms are conscious. Simply being quantum does not make something conscious. So why would quantum processes in the brain be different? The theory provides no principled answer. The fifth problem is that quantum consciousness has been exploited by pseudoscience charlatans to sell bogus products and false hope. Quantum healing, quantum medicine, quantum manifestation, and your consciousness creates reality are billion-dollar industries selling books, supplements, therapies, and seminars based on deliberately confused interpretations of quantum mechanics mixed with consciousness mysticism. The fact that legitimate scientists like Penrose propose quantum consciousness theories gives cover to these scammers, allowing them to claim scientific backing for their nonsense. This guilt by association is unfortunate for serious researchers but unavoidable. When a scientific idea becomes indistinguishable from pseudoscience in public discourse and is used to justify transparently false claims that reflects poorly on the original idea regardless of how it was intended, the quantum consciousness researchers bear some responsibility for not forcefully distinguishing their work from quantum mysticism and for sometimes using language about consciousness, creating reality that invites misinterpretation. Given all these problems, decoherence makes it physically implausible. 30 years of null results provide no evidence. Classical explanations suffice without quantum mechanics. Quantum effects do not actually solve the hard problem, and the ideas have been corrupted by pseudoscience. Any reasonable evaluation should conclude that quantum consciousness theories are wrong. Most physicists and neuroscientists have reached exactly this conclusion. They regard quantum consciousness as fringe speculation maintained by a small group of scientists who became too invested in their ideas to abandon them when evidence did not cooperate. Yet we cannot definitively prove quantum consciousness theories wrong, and this inability creates an epistemic crisis. The theories are constructed in ways that make them unfalsifiable, meaning no possible observation could conclusively rule them out. This unfalsifiability has several sources that together make quantum consciousness immune to empirical refutation. First, the theories involve mechanisms operating at scales and in regimes where current technology cannot measure. If quantum coherence in microtubules lasts a fraction of a millisecond rather than femtoseconds as calculations suggest, This might be too brief for current instruments to detect, but long enough for the theory to potentially work. If quantum entanglement spans only a few neurons rather than throughout the brain, it might escape detection while still being relevant to consciousness. The theories can always be adjusted to live in the gaps between what we can measure and what we cannot, retreating from every experimental constraint into regions that remain empirically inaccessible. Second, consciousness itself is subjective and private, making it difficult to test whether quantum effects are necessary for it. We can measure brain activity and correlate it with conscious states, but we cannot measure subjective experience directly. If quantum processes occur in the brain but we lack instruments sensitive enough to detect them, and if those processes produce consciousness in ways we do not understand, how would we know? The theory predicts correlations between quantum collapse and conscious moments, but if we cannot detect the quantum collapse or independently verify conscious moments, we cannot test the correlation. Third, the hard problem of consciousness provides a protective shield for quantum consciousness theories. Since we have no physical explanation for subjective experience, we cannot definitively rule out that quantum mechanics is somehow necessary for consciousness. Perhaps consciousness requires quantum effects in ways we do not yet understand. Perhaps the explanatory gap between brain activity and experience can only be bridged by quantum mechanics. We cannot prove these possibilities are false because we do not have a complete theory of consciousness that would show them to be unnecessary. Fourth, the measurement problem in quantum mechanics remains genuinely unresolved. Different interpretations give different answers to what causes wave function collapse and what role observers play. Copenhagen interpretation leaves measurement undefined. Many worlds avoids collapse entirely. Objective collapse theories like Penrose's remain speculative, and pilot wave theories seem contrived. No interpretation is fully satisfactory, and none can be proven correct empirically because they all predict the same experimental outcomes. This interpretational ambiguity means we cannot definitively say consciousness plays no role in quantum mechanics because we do not have a consensus view on what does play that role. Fifth, the theories can always invoke unknown mechanisms to explain away null results. If experiments find no quantum coherence in microtubules, proponents can claim the brain has protection mechanisms we have not discovered yet. If decoherence calculations show coherence is impossible, proponents can question the calculation's assumptions about environmental coupling or invoke quantum error correction that evolution might have developed. If classical explanations seem to suffice, proponents can insist consciousness involves something beyond function that only quantum effects provide. Every objection can be met with speculative responses that are difficult to test. This unfalsifiability is scientifically problematic because science progresses through testing, predictions, and rejecting theories that fail. A theory that can accommodate any observation by adjusting assumptions is not genuinely engaging with empirical reality, but is instead a flexible framework that can be molded to avoid contradiction. Karl Popper argued that falsifiability is what distinguishes science from pseudoscience. Scientific theories must make risky predictions that could be proven wrong, while pseudoscientific theories are compatible with all possible observations and thus explain nothing. By this criterion, quantum consciousness theories are pseudoscientific. They do make some predictions like quantum coherence in microtubules, but when those predictions fail, the response is not to abandon the theory, but to adjust it to avoid refutation. This pattern of prediction, failure, and adjustment without ever rejecting the core idea is classic pseudoscience. Yet quantum consciousness is not quite the same as astrology or homeopathy because it is proposed by credentialed scientists using legitimate physics and published in peer-reviewed journals. This creates an uncomfortable ambiguity. The theories have the trappings of science, but the logical structure of pseudoscience. The persistence of quantum consciousness theories, despite lack of evidence, reveals important truths about how science actually operates as opposed to how we imagine it operates. We like to think science is purely objective, following evidence wherever it leads without regard for human preferences or social factors. But science is done by humans who have psychological needs, career incentives, and emotional investments in their ideas. Once a scientist has spent decades developing a theory, published papers about it, built a reputation around it, and convinced others to work on it, abandoning that theory is psychologically and professionally costly, regardless of what evidence says. This is not unique to quantum consciousness, but is a general feature of how scientific communities operate. Thomas Kuhn showed that scientific paradigms resist change, and that anomalous evidence is often accommodated within existing frameworks rather than causing paradigm shifts. Scientists are trained in particular paradigms and build careers within them, creating inertia that resists radical rethinking. New paradigms are typically adopted not because the old generation is convinced by evidence, but because a new generation with different training and no investment in the old paradigm gradually replaces them. Quantum consciousness has become a mini paradigm with its own community of researchers, conferences, journals, and funding sources. This community has survived for 30 years despite lack of empirical support, because communities create their own social reality that is somewhat independent of external empirical validation. Researchers working on quantum consciousness evaluate each other's work, cite each other's papers, organize conferences together, and maintain belief in the program's promise despite outsiders' skepticism. This social structure sustains the research program even when the science would suggest abandoning it. The presence of high-status figures like Penrose also matters enormously. When a Nobel Prize winner endorses quantum consciousness, this lends credibility that protects the ideas from dismissal. Junior scientists might be attracted to work on quantum consciousness because of Penrose's involvement, even though most physicists reject the ideas. Funding agencies might support quantum consciousness research because distinguished scientists advocate for it. This demonstrates how scientific authority can perpetuate ideas beyond what empirical evidence alone would support. None of this means quantum consciousness researchers are dishonest or deliberately deceptive. Rather, it illustrates that scientists are human and subject to normal human psychology. We are all prone to confirmation bias, where we preferentially notice evidence supporting our beliefs and discount contrary evidence. We are all subject to sunk cost fallacy, where we continue investing in projects because we have already invested so much. We are all susceptible to motivated reasoning, where we unconsciously find ways to preserve beliefs we are emotionally committed to. Quantum consciousness researchers genuinely believe their theories and genuinely interpret evidence in ways supporting them, but this genuine belief does not make the theories scientifically validated. What should we conclude about whether consciousness creates reality through quantum measurement? The honest answer is that this idea is almost certainly wrong, but cannot be proven wrong definitively. It is wrong because decoherence makes sustained quantum coherence in the brain implausible, because 30 years of searching has produced no evidence for quantum effects underlying consciousness, because classical explanations suffice without invoking quantum mechanics, because adding quantum effects does not actually solve the hard problem of consciousness, and because the unfalsifiable nature of the theories makes them more like pseudoscience than science. Yet we cannot prove it wrong, because consciousness remains deeply mysterious, because the measurement problem in quantum mechanics is unresolved, because we cannot directly measure quantum effects at the scales where they would need to occur in the brain, and because the theories can always be adjusted to avoid empirical refutation. This creates an uncomfortable epistemic situation where we are quite confident something is false, but cannot demonstrate its falsity conclusively. What does this mean practically? It means quantum consciousness theories should not be taught as established science, or even as serious contenders for explaining consciousness. They should be presented as speculative ideas that most physicists reject, that lack empirical support, and that face serious theoretical objections. They should be clearly distinguished from quantum mysticism and pseudoscientific exploitation of quantum terminology. Students should understand that just because a Nobel Prize winner proposes an idea does not make it correct, and that science requires evidence, not just mathematical elegance or famous advocates. It means research resources should not be devoted primarily to quantum consciousness, given the low probability it is correct, and the abundance of more promising approaches to understanding consciousness through neuroscience, psychology, and classical computational modeling. Some small amount of exploration might be justified on long-shot bets, but quantum consciousness should not be a major research program consuming substantial funding and scientific talent when evidence does not support it. It means claims that consciousness creates reality should be viewed with extreme skepticism. While quantum mechanics does involve observers and measurement in subtle ways, there is no evidence that consciousness specifically plays any role in quantum collapse. The measurement problem can be addressed through decoherence, many worlds interpretation, or other approaches that do not invoke consciousness. Claims that your consciousness collapses wave functions and creates reality are not scientifically supported and should be rejected as confusion or deliberate misrepresentation. Yet, it also means we should maintain some intellectual humility about consciousness and quantum mechanics. Both involve deep mysteries we do not fully understand. The hard problem of consciousness remains unsolved, despite enormous neuroscientific progress. The measurement problem in quantum mechanics remains unresolved, despite a century of quantum mechanics. It is remotely possible that these mysteries are connected in ways we have not imagined, that future discoveries will reveal links between consciousness and quantum mechanics that current physics misses. This possibility is sufficiently small that it should not guide research priorities, but sufficiently non-zero that we should not be absolutely dogmatic. The consciousness-quantum connection debate reveals the limits of science when confronting subjective experience. Science excels at explaining objective phenomena that can be measured, quantified, and tested. Consciousness is fundamentally subjective, experienced from first-person perspective, and seemingly irreducible to third-person objective description. This creates a methodological challenge for science that quantum consciousness theories attempt to address by invoking quantum mechanics' seemingly subjective, observer-dependent features. But this attempt fails because quantum mechanics is actually objective once properly understood. The observer dependence is about what information is available, not about consciousness creating reality. The real lesson is that consciousness might require explanatory approaches that differ from standard reductionist physical explanation. This does not mean consciousness is non-physical or supernatural or mystical, but it might mean consciousness is real in ways that cannot be captured by standard physical theories. Philosophers have proposed various frameworks, including panpsychism, where consciousness is fundamental rather than emergent, dual aspect theories where mind and matter are two perspectives on one reality, or emergent property dualism where consciousness emerges from physical systems but has irreducibly mental properties, not reducible to physics. These philosophical approaches might or might not be correct, but they illustrate that multiple conceptual frameworks exist for thinking about consciousness beyond either materialist reductionism or quantum mysticism. We do not have to choose between consciousness is just neurons firing and consciousness collapses quantum wave functions. Alternative conceptual frameworks might better capture the relationship between subjective experience and objective physical processes without requiring either reduction or quantum intervention. In practical terms, quantum consciousness theories have had minimal impact on actual neuroscience or psychology. Researchers studying how the brain produces consciousness focus on neural networks, information integration, global workspace theory, and other classical frameworks that have proven productive for understanding cognition and consciousness. Quantum consciousness remains on the fringe, interesting to a small community, but ignored by mainstream consciousness research because it has not produced useful insights or experimental programs that advance understanding. This pragmatic irrelevance is perhaps the most damning verdict. Even if we cannot prove quantum consciousness theories are wrong, the fact that they have contributed essentially nothing to practical understanding of consciousness after 30 years suggests they are not productive research directions. Science judges theories not only by truth, but by fruitfulness. Do they generate new predictions, open new experimental directions, and advance understanding? Quantum consciousness theories have failed by this criterion, regardless of whether they are strictly false or merely unproductive. So where does this leave us personally in understanding consciousness and our place in reality? Should we believe our consciousness creates reality through quantum measurement, or that we are classical information processors? The scientifically justified position is that consciousness almost certainly does not involve quantum mechanics in any fundamental way, that subjective experience emerges from classical neural processes through mechanisms we do not yet understand, and that consciousness does not play any role in quantum collapse or reality creation. This position is less romantic and less flattering to human specialness than quantum consciousness theories. It suggests we are not cosmic observers whose consciousness is required for reality to exist, but are instead localized biological systems whose consciousness is a remarkable but purely natural phenomenon produced by evolution. It suggests the hard problem of consciousness is difficult but not impossibly mysterious, that future neuroscience will progressively explain more about consciousness using classical physics and biology without requiring quantum mechanics or new fundamental physics. Yet this scientifically justified position remains tentative because consciousness is genuinely mysterious and science is incomplete. We should proportion our confidence to the evidence while remaining open to surprises. The evidence strongly suggests quantum consciousness theories are wrong, but we should not be absolutely certain. This intellectual humility, combined with skepticism toward unsupported claims, is the appropriate scientific attitude, rejecting quantum consciousness as the most probable answer, while not completely closing the door to remote possibilities. The quantum consciousness debate ultimately reveals both the power and limits of science. Science is powerful at testing physical theories about objective phenomena and has conclusively shown that quantum effects almost certainly do not underlie consciousness in the ways proposed. But science has limits when confronting subjective experience and may require conceptual frameworks beyond current physics to fully explain consciousness. Recognizing these limits without abandoning scientific rigor or embracing pseudoscience is the challenge. Does consciousness create reality through quantum measurement? No, almost certainly not. The physics does not support it, the evidence does not confirm it, and better explanations exist without invoking quantum consciousness. Should you believe claims that your mind collapses wave functions and manifests reality? No. These claims are not scientifically justified and are often deliberately misleading. Should you completely rule out any connection between consciousness and quantum mechanics? Not absolutely, because both remain mysterious and intellectual humility is warranted, but the connection is so unlikely that it should not influence how you think about consciousness or reality in practical terms. The persistence of quantum consciousness theories, despite their implausibility, teaches us about human psychology, about how scientific communities operate, about the appeal of mystery, and about our need to feel special and significant in the cosmos. These are interesting lessons even if the theories themselves are wrong. Understanding why false but appealing ideas persist is part of understanding ourselves, which is ultimately what consciousness research aims to do. Perhaps that self-understanding is more valuable than the quantum consciousness theories themselves, which may be their only lasting contribution to knowledge.